Welcome. Prepare to be amazed. Today we're going to be doing one of the coolest things I've ever seen in mathematics. I've seen a lot of cool things, but this is one of the cool things that I love. So we're going to be dealing with the function e to the x. You know how to work with it. You've seen it in calculus, you've seen it in algebra. But now instead of plugging in a number, which you very well know how to do, if I plug in 2, I get e squared, for example. We're going to step it up a notch. We're going to plug in a matrix. That's right. A matrix. What in the world does that even mean? How do you plug a matrix into e to the x? And why would you even consider that? So before I ask you why, first of all, let us ask the question, what does that even mean? Well, the only way that you can actually define this is by plugging into the Taylor series of e to the x. You know the Taylor series, you know it from calculus. What you're going to be doing is you're just going to be plugging a matrix in here, and that makes some sense. There's some things you got to worry about, like why it converges, but let's just skip all that for a moment and see what that gives us. So a to the k is you're just multiplying a k times. So then if this converges, then all of this actually makes sense. Let's go ahead and do that with a nice example. So we're given this matrix, 3, 1, 1, 3. Computing a square, not that bad. You can do it. You can even do a to the 3. Not that bad. But what about a to the 2019? That's going to take you a long time. But if you're dealing with diagonal matrices, such as, 2, 4, 0, 0, then that is a lot easier. Computing d squared is just 2 squared, 0, 0, 4 squared. And also computing d to the 2019 is going to be 2 to the 2019 and 4 to the 2019, 0, 0. So hence, it is nice to compute e to a matrix when the matrix is a diagonal matrix. And what's really nice is that you can actually diagonalize a lot of matrices. And what we mean by diagonalizing it is we want to write a matrix in the form E times D, where D is diagonalized, a diagonal matrix times E and its inverse. And diagonal matrices are exactly what we have here in the top, where you just have zeros outside of the diagonal. So we only care about non-zero entries here. Or they can also be 0, but the point is that you want 0 everywhere else. And so sometimes you can do that. And the way you want to find this composition is you want to look for its eigenvectors and eigenvalues. So we've done the work for you guys. So we're going to go ahead and call V1 negative 1, 1, 1, and V2, 1, 1. This is the eigenvectors corresponding to lambda is equal to 2 and lambda is equal to 4. So I'll call this one the first eigenvalue, and this is going to be the second one. So if I were to multiply A by this convenient matrix whose entries are exactly the entries of the eigenvectors, what happens? Well, I multiply this through. The way this is defined is the first column is replaced by the product of A and V1, and the second one by A and V2. What you're going to get is lambda 1 times V1 because it's an eigenvector, and lambda 2 times V2 because it's also an eigenvector. And then you can break this up between V1, V2 times this diagonal matrix, V1, V2, 0, 0. And you can go ahead and verify that this actually indeed works out. So what we call this is going to be E, and this is going to be our D. And here on the left is AE. So since these two eigenvectors correspond to different eigenvalues, we know they're linearly independent. Therefore, E is invertible. Therefore, we can write A as E times D times E inverse. Okay, so now we can go ahead and plug it in to the Taylor series. So in order to do that, we're going to be needing A to the K. So check this out. Before I tell you what A to the K is, let's just do it for A squared and see what happens. Using this way of writing it, we're going to have E D E inverse times E D E inverse. Notice here in the center, there's going to be this cancellation thing. So you're just going to get E D squared times E inverse. So moving this off to the side, making it nice and small, going back up here, now A to the K, it's not going to be that hard to see that in reality it's just E times D to the K times E inverse. And let's go ahead and zoom in on D to see what's happening, because in reality, we want to plug this into the Taylor series. And so when we plug this into the Taylor series, we want to focus in on what's happening within the entries. So in the entries, let's remember what D is. D is 2, 4. So we have here 2, a 4, and then 0, 0. So let me go ahead and bring this out here and make it a little bit bigger so we can all see. We're going to have a K here at the top left, and at the bottom right, we're also going to be having a K. What we also need for the Taylor series, we're going to need to divide by K factorial. So it's just a scalar, so let's do it term by term. That's what we're supposed to do. Here we go, and here we go. The next thing that we do is we're going to be adding. We're going to be introducing the summation. Well, how do you add matrices? Term by term. So let's go ahead and do that. Term by term. So we have K going off from 0 to infinity. K going off from 0 to infinity. K going off from 0 to infinity. Well, what do we have here in each of the components? This is just the Taylor series for e to the x, so it's just e to the 2. Here we have e to the 4, we have a 0, and we have a 0. So now going up here, remember we're plugging in a, but a is just this. So what we're missing here is e, and let me make some more room here. We're going to need an e inverse here. We're going to need an e here, e inverse, e, and e inverse. So this here is e to the a. So if we're interested in e to the ta, you can follow the math, and in reality, all we do is just have e to the t2, 0, 0, e to the t4 times e inverse. There you go. This is one of the coolest things that I have seen, is plugging a matrix into a function. But then you want to ask the question is, why in the world would you do that? And that's because this is going to help us solve this system of ODEs. So you've seen the system of ODEs. How do you solve it? Well, you can actually check that this is going to give you a solution. How would you construct your solution? You're going to take e to the ta and you're going to multiply by constants. So we're in the 2 by 2 case, so we just need two constants, C1 and C2. This here is your general solution to the system of ODEs. Now, if you had initial conditions, say like you plug in 0 and then, I don't know, 2019 and 2020, if we want to solve that, well, we want to plug in 0 to this. What do we get? E to the 0 times a times this constant vector. It's just e to to the 0 matrix times C. And what you're going to get is the identity. How do you know that's true? Well, go ahead and plug in 0 to the Taylor series. Follow the algorithm going on here, and that's exactly what you're going to get. So what is our constants? It's going to be exactly that. So then our solution is going to be, with this initial condition, is going to be e to the ta times our initial condition. Awesome. Thank you for joining me.